Hey, thanks for watching our SIS 2450 final presentation where we made a weather prediction model to trade on the Cauchy daily high temperature markets. So we'll start just going over the task. So we're basically taking in past weather and atmospheric data, trying to predict the max temperature, and then execute Cauchy trades based off of that. So hopping into the data, we'll start with kind of where we got our data from. So we got our data from two data sources, Open Meteo and Power. Open Meteo is hourly historic temperature, wind precipitation data. NASA Power is atmospheric radiation and soil data at a daily granularity over the past years.
So starting with Open Media, we had the following four data sets that we had. We were looking specifically at New York throughout this project. We had the temperature measured hourly, the wind speed, the wind gusts, and the precipitation amounts. And just to give you a sense for this data set, so because hourly, there's a lot of data here. You could see here that we're just looking at days over the last several years, and you can see it follows a clear seasonal trend, hotter in the summer, colder in the winter. This is the maximum temperature of every day. But even within that, in the top right, you can see that a single day has its own trend of being cold at night and being hot during the day. Uh, Looking at the wind, you can see there's also some correlation. There's looks like more wind during the winters, perhaps, and then precipitation. It's got a little bit less regularity, but something to note with the precipitation data says not every day has precipitation, so there's some zeros in that data set.
And then for the sake of time, I'm kind of going to go through this quickly, what we pulled from NASA Power. But we basically pulled different combinations of solar radiation and thermal radiation coming into the atmosphere. So different measurements on that, as well as measurements on how much stuff is in the air. So that's the aerosol optical depth. And then also the humidity in the soil to kind of get a grasp of humidity because that affects the atmosphere warming and cooling each day. And then you can kind of just see here, each one of these also actually similarly kind of follows that seasonal pattern, which actually creates a lot of multicollinearity for us, which you'll see later.
So to create our data set, we basically pulled from our sources. The NASA data, we had to do some cleaning because there's some nulls there. So we just filled those with null. And then we joined by day. So for each hour of our hourly data set, we joined the day with the days of the NASA features. And so that was a way to combine those two data sets. The features that we started with were the ones on the left with the temperature, the max temperature, wind, precipitation, etc., as well as all the NASA, artifacts, the features from there. We created some features of our own, so the day, month, and then the average temperature. Then we had some lags, so those were basically the max temperature from the day before that, etc. And then we also had a rolling average of the maxes over the last several days, 3 days and 7 days, as well as the precipitation. We had a lag feature. And the label we're trying to predict is the max temperature tomorrow. And so here's just to give you a sense for what this data set sort of looks like. You can see a few rows and the values associated. And to get a sense for the correlation of our features, you can see that a lot of the temperature features are very correlated. You can see we have a lot of multicollinearity, but some features are less correlated, like wind and temperature and things like that. There's some negative correlations related to humidity versus temperature, things like that. And then you can see the number of rows that we have throughout our data set creation pipeline changes. So the Open Media being an hourly data set, we have a lot of data. The NASA one being daily before cleaning, and then after cleaning, there's only a little bit of rows we had to remove, just because it was mostly okay. But after joining them, it was a join using like the Open Media rows, so it basically stayed exactly the same. And then our daily model data set is similar in size to our NASA data set, given that it's just based on daily. And you can see that after we drop the nulls, it only decreases a small amount. Here's another visualization after we, took all of the data, the distribution of the tomorrow's maximum temperature. It's sort of a normal distribution.
Yeah, now we're going to hop into modeling. And just to kind of clarify, so we've collected all this data and we've created two separate data sets from the data. We've created an hourly data set. So that's the hourly temperature at each hour, and then copying the NASA data throughout each day at the hourly level. And then we also have a daily data set. And that's the data set where we created the lags and the rolling averages. So the first two actually, the first three models we're going to show you all use that daily data set. And then lastly, that transformer is what's using the hourly data set.
So our first attempt was a k-means model, k-means plus plus. We thought that because weather is very similar, year like from one year to another, perhaps that we could do some clustering and then look off of that, do PCA. But you can see here that there's no clear elbow here. It's a very continuous data set, and our error was not exceptional here, as you'll see with our later models, they only improve. So then we decided, okay, we should do instead of unsupervised, we should switch to some supervised. We did a normal linear regression. It had a much, better errors, better like statistics with the error, but there's a lot of multicollinearity, so we had some huge coefficients, and so we ended up doing a ridge regression with a grid search on the L2 penalty coefficient, and we ended up with 10 as that, and it improved. And you can see that our coefficients stabilized here. And so, yeah, our mean absolute error here, four degrees Fahrenheit, and mean squared error 6.
Yeah, and then kind of to try and deal with these interactions between each feature and kind of the high multicollinearity and also uh, the nonlinear patterns of weather, we decided to go with a random forest regression. Um, And also for explainability, it's also great at kind of seeing what features are important. And this did pretty good. So then we took this and did a hyperparameter optimization. So we did a randomized search across number of trees, the max depth, the minimum samples per leaf, and the max features per tree. And you can see kind of the best parameters we ended up with on the bottom right. And this was able to train super quickly. So it wasn't really, or sorry, whatever it trained, and you can see um, each of the factors slash features that this prioritized, and it was actually relatively similar to the same features that ridge regression used, and the error was also relatively similar to ridge regression. And then finally, kind of for our big model, we created a transformer architecture, which this basically created windows. So it's kind of like a sliding window of weeks. So it would give 168 hours, which is 1 week worth of data in a time series format. Input that, and then try and predict the next day's max temperature. So we used a transformer encoder architecture. We started kind of with a input projection, which was basically a learned embedding. Also added a positional embedding to that, and then outputted tomorrow's max temperature. And the loss in the learning of this actually went really well. So it was learning really well, fitting very nicely. We then also did a randomized search since the training for the transformer was kind of slow. So we didn't want to do a grid search. We did a randomized search. You can see the best parameters we ended up with over there, kind of messing with the hyperparameters as well as the attention heads and the embedding dimensions. And this is what gave us the best mean absolute error and root mean square error out of all of the models. And then kind of one note there is we tried adding a ReLU after the embedding before the transformer, but that actually decreased performance. So we didn't use that.
So here's just a visualization of the transformer's uh, performance, and it's very clearly, mirrors the data pretty well. And you can also see here our test set error by model, and you can see it just improves over time. Yeah. And so now just to look at our overall results. So our Kalshi results were relatively good. Actually, the transformer didn't perform that well on Kalshi, but the ridge regression and tune random forest were better than random, and so we were pretty happy. Some limitations was that our Kalshi bot only traded once per day, so we thought maybe training on like being able to trade Kalshi hourly, would be an improvement, as well as we don't have hourly atmospheric data, we just have those daily data sets. And some other improvements, perhaps for the transformer, we could use a larger time window, not just that 1 week time window that we gave it. As well, we only looked at New York City here, so to look at being able to generalize it across cities. And then additionally, we thought we could collect Kalshi trading data to be able to perhaps train a model specifically on the trading side.
And just lastly, one quick note, just for context, all the models were trained up until 2024, and then the test set was everything after 2024. So we kept all those times, the training and the testing times totally separate, so there was no training on future times. But yeah, that's everything. Thanks for listening to our presentation, and have a great day.